Good morning or afternoon. This is Mrs. Sharp, and I am pleased to tell you that these notes, which are 5.3, Part 2, are going to be our last notes of the year. So, with that in mind, I'm very excited to give you these, your very last notes, and we're going to talk about some standard reduction potentials. And this is going to make use of that table that I gave you in class that is on the other side of your drawing of the electrochemical cell. So let's talk about what standard reduction potential means. So the standard reduction potential, or EMF, is the tendency of an electrode to gain electrons at standard conditions. Standard conditions in the case of an electrochemical cell are when you have a 1 molar solution at 1 atmosphere of pressure and at 25 degrees Celsius. So it's a relative measure of the tendency, so how badly an electrode wants to gain electrons or be reduced, that's why it's called the standard reduction potential, at standard conditions. It is measured in volts as compared to a standard hydrogen electrode. So a hydrogen electrode being reduced is going to have a standard reduction potential of 0. So everything else is relative to that. So the higher that number is, the more likely it is to be something that wants to be reduced. And so anything higher than 0 that's positive is going to be more likely to be reduced than hydrogen. Anything that's a negative value is less likely than hydrogen to be reduced. So one thing I want you to notice there is at the top of your table, the very highest standard reduction potential is fluorine going from F2 to F-1, or an oxidation number of 0 to having an oxidation number of -1. And that's because fluorine has such a high electronegativity, remember, it's got the highest electronegativity on the periodic table, that it's very likely to want to draw those electrons to itself with that high electronegativity, which is why it's got a really high standard reduction potential. If you look at the bottom there, lithium has the lowest on your list, and that's because lithium would rather stay a +1 ion. It doesn't want to be reduced. It's very stable as lithium +1, because that means that its electron configuration is like a noble gas. So it really doesn't want that other electron. It's got a really low electronegativity because of that too. So it's also got a low standard reduction potential. So it all kind of ties together. Now, one thing that your professor may want you to do in the future is to calculate what's called a standard cell potential. And this is when you know what's going on in the cell and you want to figure out how much voltage is going to be generated through that cell. So thinking about our example from yesterday with the zinc that was being oxidized and the copper that was being reduced, how much voltage would we actually generate as we got that electrochemical cell working? And so we're going to do that example for these steps. So the first step is to write each half reaction as a reduction and look up the standard reduction potential. So even though we know they're not both being reduced, we're going to write it that way because that's what we're going to find on our table. So our reductions are going to be Cu plus 2 and 2 electrons, making Cu 0. And then we're also going to have Zn plus 2 and 2 electrons, making Zn 0. Okay, so those are our 2 half reactions. Okay, so for copper, I just looked that up on your table, and for copper being reduced from +2 to 0, the standard cell reduction there, or standard reduction potential for that half reaction is 0.34. And for Zn plus 2 becoming Zn0, that being reduced, 0.76. So of those two, the one that is more likely to occur as a reduction is your copper plus 2 because it's higher, which means this is actually going to become an oxidation. So this is number 2. It says the higher value potential will take place as a reduction, so rewrite your half reactions to reflect this. So what I'm going to do is take this second reaction, this Zn plus 2 electrons, and I'm going to rewrite it as the oxidation, so that I have Zn 0 becoming Zn plus 2 and liberating 2 electrons. And since we're just reversing that process, that means the sign would also reverse of our standard reduction potential because it's just taking place now in the opposite direction. So the overall standard reduction potential of the cell, or the cell potential, is when we take those two values and we add them together. So we have our 0.34 for our reduction, and then our oxidation is 0.76. So those two numbers together are 1.10 volts. And that's a positive, of course. And then just 4 and 5 are some tidbits of information. If that number, the cell potential, the standard cell potential, is greater than 0, that means the cell is going to generate that voltage spontaneously. It's going to go ahead and just run itself, and it's going to generate that voltage. And when that happens, it gets a special name. That cell is called either a voltaic cell or a galvanic cell. So that's if it ends up being positive. Now, if it's negative, which if you are looking at those values and deciding what is oxidized and reduced, you shouldn't get that. But sometimes the problem will just specify automatically what is happening. And you may calculate a negative standard cell potential. Now, if that happens, all that means is that the cell is actually going to require a voltage in order to occur. And that also has a special name. That's called an electrolytic cell. So it just means it's going to have a deficiency of voltage. It's going to require that much voltage in order to get that reaction to occur. Okay, so as a final example here, I'm going to give you a cell notation, and I'm going to have you calculate the standard cell potential. So we are going to have, remember, a cell notation tells a little story. So we have here cobalt being oxidized into cobalt plus 2, and then chromium plus 3 being reduced to chromium 0. And so the question would say something like, calculate the standard cell potential for this cell. And so remember that the first thing you want to do is write your half reactions, but you want to write them as both as reductions, since that's what's going to be on your table. So even though this is the oxidation, we know that that's the oxidation, this is what it's going to look like on our table, so we'll write it that way. And we've got our chromium being reduced. And we'll go ahead and look up those values. Okay, so I have looked up those values on your table, and the standard reduction potential for cobalt plus 2 becoming cobalt with a 0 oxidation number is negative 0.28, and for chromium plus 3 becoming chromium 0, we have a negative 0.41. And our next step is to rewrite our oxidation. Now I want you guys to see something. This cell is dictating that our oxidation is happening in our cobalt. Okay? Now, based on what we see here, the higher number should be the thing being reduced, which is cobalt. So that would be if it's going to happen spontaneously, it should do it that way. So that's a clue right there that this is probably going to end up negative, which means the cell is going to be electrolytic, meaning it's not going to be spontaneous, it's going to require voltage. So our cell is dictating that our oxidation is happening in the cobalt. So I'm just going to rewrite that to reflect cobalt being oxidized. So cobalt becoming cobalt plus 2 and 2 electrons. And remember, that's going to change the sign from negative now to positive. So now that I have these rewritten correctly, these can just be added together to get the overall cell potential. And so what we're going to get is a negative 0.13 volts. So this is going to be an example of a non-spontaneous cell that's going to require voltage, so it's going to be called electrolytic. Now as far as the overall, remember if I wanted to take, this has no bearing on the cell potential, but if I wanted to write the overall redox reaction for this, I would have to make sure my electrons balance. So again, that has no bearing on these cell potentials. It doesn't matter, but if I was going to write this correctly, I want to make sure my electrons balance, which means I would need to multiply that guy by 3 and that guy by 2. So overall, here I would have 3 COs plus 2 Cr plus 3s, and then of course my 6 electrons there, making 2 Cr0s plus 3 Co plus 2s plus 6 electrons, and then those electrons would cancel. So I would still need to do that for the reaction, for the overall reaction, but it doesn't come into play when you're calculating your standard reduction potentials. Or, excuse me, your standard cell potentials from your standard reduction potentials. So I think on that note, I need to be done. So I hope that that was informative for you and that you feel like we've got a pretty good handle on starting to calculate some of these standard cell potentials, and we'll work on it in class 2. So there you go. Have a great rest of your day.